Let's take a look at number 7 here. It's actually a pretty quick one when we get it set up as far as the integration goes. We're going to find the volume of the solid obtained by rotating the region enclosed by the graphs of functions x equal the square root of y and x equals 0 about the y-axis over the interval of y values from 1 to 9. Okay, so we do need to interpret this a little bit to get it set up. Once we get it set up, it's going to be quite easy. First of all, I want you to note that if x is the square root of y, if I square both sides, of course, I get y is equal to x squared. Of course, provided x is only what? Non-negative, right? Because obviously if I take the square root of some value, x will have to be a positive quantity, since that's the range of the square root function. So this is just really one branch, if you will, of the parabola y equal x squared. Now, on the interval from 1 to 9, what do we have? When y is 1, clearly x is 1. And when y is 9, the square root of 9, x is 3. So we plot those points, and you can see they're, of course, on the graph of x equal the square root of y. So why did they list it as x equal the square root of y as opposed to y equal x squared? Well, we're going to have to integrate with respect to y in this case. We're rotating this region. Of course, it's bounded by this curve and x equals 0. Remember, x equals 0 is a vertical line. In fact, it's the line that coincides with the y-axis. Okay, so on the interval of y values from 1 to 9, I've shaded in the region we're talking about. And we're rotating that region about the y-axis. So this region will flip back in and we'll get that solid, looks like some sort of dome shape that has a topped off. We're going to flip it around this way, right? Flattened off at the top. So we are using the disk method here, and so I'm going to integrate actually with respect to y. And that's why we need to have these functions that are bounding our region as x is a function of y. Notice this region is not vertically simple, but it is horizontally simple, right? It's not vertically simple because the bottom function changes as you're going from left to right, from this constant function y equal 1 to this curve. But if I look at it going, the left to the right horizontal lines will always have the same two functions, right? So it's horizontally simple. So we're going to use the disk method, and I've got an arbitrary rectangle. Notice it's horizontal since I'm, partitioning this axis up from 1 to 9, and I'm looking at those rectangles. As this rectangle rotates, comes out of the page, back into the page, and back around, we're going to get what? That disk right here. And that radius r is just the length of this line. It's of course, this is the x length, and that's why we need to know the x value. So it's from x equal the square root of y to x equals 0. Well, square root of y minus 0 is indeed the square root of y. So that radius is just the square root of y. That's the distance. And notice it's true, right? When y is equal to 1, what's the square root of 1? 1. That's the x distance. And when y is equal to 9, what's the square root of 9? 3. That's this distance here. So it's going from a length of 1 or radius of 1 to a radius of 3 as we move from y equal 1 to 9. So the area of the disk is pi times that radius squared. The radius is the square root of y. We just get pi times y, which is really easy to integrate. So here it is. We're going to integrate pi times y. I pull the pi out from y equal 1 to y equal 9. And this is our easy integral to do. Quick antiderivative of y is 1/2 y squared. Plug in 9, plug in 1, subtract, simplify. We get 40 pi. Pretty easy as pie.